Okay, so we already in week 12 and we have two weeks left for this semester, and I have discussed with Dr. Izani. So we are not going to do the last chapter as I've mentioned last week. You will skip that last chapter concerning thermodynamic of a high speed gas flow, about the nozzle, something about compressible flow, because actually that topic, yes, it also concerns thermodynamics part, but as far as we know, it will be also covered in aerodynamic 2 next semester. You guys are going to take aerodynamic 2, which concern about compressible flow, normal shock waves, oblique shock waves, and then some that part also I think will be cover a bit in about the nozzle, will be cover a bit in space launch. Space launch technology, that course is in your semester 6, so about more than 1 year more to come. Okay, so we will skip that last chapter. So we have left with three chapters. Three chapters actually, but I will combine it into two chapters. This one, Entropy, and next week inshallah concerning gas power cycle. Okay, one of the most important part, because that concerns the main the Brighter cycle. Okay, gas power cycle is the main cycle for aircraft engine. That one will be your main application in propulsion course next semester. Okay, so that is very important. So that one we have to include. We have to finish that also. So we have left with 2, 3 chapters more this week and next week. And the last week, week 14, we will do revisions. Okay, to prepare for the final exam. Okay. So wait. Okay, so your final exam is for aerothermodynamics is on 11th 11 February, if I'm not mistaken, 11 February, 3:30 to 5:30 p.m. Friday. Okay, the first week of your final exam. And as I've mentioned also in the WhatsApp group, I have postponed, okay, the deadline for the assignment, the last assignment that I gave you last week. Okay, since we have just received information from Vice Chancellor Academic, that we can that students can submit all the assignments, okay, coursework, until the last week of final exam. So I've postponed that deadline until 18th February. So that is the last date. So you have extra 3 weeks more than previously what I have mentioned. Okay. So you have total of 6 weeks, 1 month and a half to do that assignment. So if you have any questions or anything, any problem concerning that assignment, please refer to me. Please WhatsApp me or email me, or okay, or you can set a date if you want to meet me at the office. Okay. Maybe not all the time at the office, but you can set time and date if you want to discuss anything with me. I'll try to come to the office. Okay. Okay, so without any further ado, we will continue this chapter, entropy. Last week we have seen about, I have introduced to you about second law of thermodynamics. Okay, second law of thermodynamics. Okay, you have first law during the first half of the semester, and then you have second law. Okay, why do we need second law? Because second law generally, okay, a second law will help us help us to identify the quality of a process, of any thermodynamic process. Okay, it helps us to identify the quality of the process. The quality means that it identify the irreversibility the process that is not reversible. Okay, the reversibility loss of the process, energy loss of the process. Wait, someone at my door, je, eh. Okay, continue. Okay, so second law help us to identify the irreversibility, the energy loss in a process, which cannot be identified by just using the first law. Okay, the first law, energy balance. Okay. So entropy. So entropy. Okay. Okay. So in the first law, to evaluate, to calculate the first law, we have that parameter enthalpy, H, noted as H. Remember, the H is enthalpy. It's in kilojoule per kilogram. Okay, that enthalpy is one type of energy. Okay, that we use to calculate the first law, in the first law. Okay, enthalpy, to calculate the energy balance. Now for the second law, we introduce another parameter, another new parameter that I have somehow show to you before, which is entropy. Okay, so entropy is used to calculate the second law. Okay, entropy. So entropy is noted as S. Okay, the letter S. Okay, so when we draw the TS diagram, temperature versus S, which is entropy. Okay, so this is concern the second law, entropy. Yeah. So this topic, we will see how are we going to use this entropy to calculate the energy loss, okay, of a process. Okay, so what is entropy? Okay, so okay, if you see from the left hand side, you see the level, the range of the entropy, solid, liquid, gas. Okay, so generally the gas has higher entropy than liquid, and then compared to solid. Okay, the level of molecular disorder, entropy of a substance increase as it melts or evaporates. Okay, in a simple word, okay, entropy, what is entropy? Entropy is level of molecular disorder. Okay, the disorder, the okay, the disorder of the molecules. Okay, so that's why gas has higher entropy than liquid and solid, because gas has a higher speed, velocity, and the molecules can move faster. Okay, so it has potential to have a level of molecular disorder higher. Okay, as for gas. So this is what entropy is all about. Okay, so when if a process, when we in second law we say that the process cannot be reversible, means irreversible, due to the friction, due to the fast movement of the process. Okay, So this creates the friction, etc. Creates the makes the process irreversible, cannot be reversed back, cannot be turned back to the initial location, initial point, or initial situation, initial state. Okay, the process cannot be reversed back. Okay, so the process cannot be reversed back. One reason is due to the friction or and any other reasons. Okay, so so it causes the irreversibility. So entropy, this parameter, we are going to quantify. Okay, like somehow like measure this level of irreversibility. Okay, this level of non-reversible, this level of the energy loss. Why for example, why the process cannot be 100% efficient, or why it cannot be reversed back. So the level of this irreversibility is calculated, is measured by using this parameter entropy. Okay, so that's why this entropy links with second law, the irreversibility of a process. We are going to calculate how much the level of irreversibility of a process. So of course means that we want in order for the process to be ideal, to be better. Okay, of course we want to reduce this entropy, this value of entropy, because entropy means energy loss, irreversible. So we want to reduce an entropy of a process as much as possible. That is the idea. Okay. So Boltzmann relation. So we have this relation K LMP, but we will use other relation as well. Okay, so this is entropy. A pure crystalline substance at absolute zero temperature is in perfect order and its entropy is zero. Okay, so this is example of a pure crystal if with zero entropy, means no energy loss. Okay, and then at the bottom one, disorganized energy does not create much useful effect no matter how large it is. Okay, this is just an example of a people pulling a load at different direction, so the load won't move. Okay, berat tu takkan bergerak pun, or load won't move. Okay, so means that the disorganization of the of this thing, okay, disorganized, they didn't organize properly how to move the load. They should have pull it from only one part, either part, but they pull it at both ways, means disorganized of management. Okay, so this resembles the disorganized of energy. Okay, does not create much useful. So if we have for example a group or a company or a group with not well managed, which is disorganized, so it will not create any useful output, okay, from this group. So this is the same as in energy process. If the process is disorganized, the disorganized energy, it won't create much useful effect no matter how large the energy we put. Okay, so the same thing as in our teamwork or in a group or in organization. If we don't organize well our work, our team, even though we have extra manpower, it will not create much useful outcome. Okay, so you can imagine that is what entropy is all about. Okay. Okay, for example here we have the essence of friction. Raising a weight by a rotating shaft does not create any disorder entropy, and thus energy is not degraded during this process. Okay, so for example, friction is one of the factor that can cause irreversibility, non-reversible of the process. So if there is no friction, which is impossible, okay, but there is an ideal case, okay, absence of friction, no friction, so the weight can be lift up, okay, by the rotating shaft, okay, and it will not create any disorder, any entropy, okay, no energy loss because absence of friction. Okay, no energy is degraded. Energy is not degraded during the process. Okay, so entropy means also degradation of energy loss, degradation of energy. The pedal wheel work done on a gas increase the level of disorder of the gas, and thus energy is degraded during this process. Okay, another example where there is energy loss, there is entropy level. Okay, because the gas, the movement of the gas, molecule of the gas inside here. Okay, when we have the pedal wheel work, the work given, okay, the shaft work given, introduced to the gas inside, so it will degrade it, it will touch interrupt the movement, the velocity, the speed of the gas, so it will create a level of disorder of the gas. It interrupts the normal speed of the molecules within the gas. Okay, during a heat transfer process, the net entropy increase. The increase in the entropy of the cold body more than offsets the decrease in the entropy of the hot body. Okay. Okay. When we during a heat transfer process from hot, of course, from hot to cold body, from hot material to cold material. Okay, there will be some sort of entropy loss during the process. Okay, means that even though for example here the hot body is at 80 degrees Celsius and the cold body is 20 degrees Celsius, not all of the energy, okay, the thermal energy within the hot body will be transferred to the cold body. Not all these 80 degrees Celsius will be totally transferred and then this cold body will become 100 degree. No, okay, there will be somehow energy loss during the heat transfer process, so only maybe a portion of the hot body, okay, will be the energy from the hot body, the warm temperature will be transferred to the cold body. Okay, not all. Okay. Okay, so this is more interesting part. So what is so how to calculate? Okay, how to measure this irreversibility, this entropy? Okay, so we have this TdS relation. T is temperature, ds the differential of S, entropy, the small s entropy. So we use like enthalpy, the first law. We use the mass, the per mass meter. So we write it in small letter, not capital letter. We can use the capital letter S, but that means that it is in kilojoule per Kelvin. But if you write small s, means it is in kilojoule per kilogram per Kelvin. Okay. Okay, so we use this TDR. So that's why we always draw the TS diagram. Temperature versus the graph, temperature versus S entropy, because it results from this TDS relation. Of course, when we integral of this DS, we have S. Okay, so we have this equation. Okay, so for a closed system, the TDS relations are valid for both reversible and irreversible process, and for both closed and open systems. Okay, this is a closed system, example of a closed system, piston, and this is an example of open system, control volume. So we have this control volume of, for example, nozzle or turbine. Okay, turbine, for example. So turbine, the process, the system is open, but we still we determine the closed volume, the control volume, sorry, CV, control volume. Okay, so this is open system. For example, turbine process. Okay, so the mass can inlet outlet. Okay, open process. And for both, this TDS relation are valid for both reversible and irreversible process. So that's why it can be used to measure the irreversibility of a process. Okay, because we can use the TDS relation for irreversible process, not only for reversible. So it can be used in second law. Second law, okay? So we have these two, very, very important. Okay, even though you don't need to memorize, but if you use it several times, one day you will memorize this equation. Okay, so we have these two forms of TDS relation. So from this relation that we have this entropy equation, okay? T temperature, ds is the differential of the entropy, means that the small change in the entropy, okay, equals to du, the internal energy. Okay, remember first law thermodynamics, we have internal energy, U. Okay, the differential of U plus PdV, P pressure, and V here is volume. Volume, not velocity, volume. Okay, PdV is a volume. Okay, and we have another one, okay, TDS again, but this time linked with enthalpy. Okay, enthalpy dH minus V volume dP. Okay, these two are the relation for entropy. Okay, so we have two types of relation. Okay, so how are we going to develop? We can rearrange this equation and develop this equation. Okay, first one, okay, du. What do we know about du? Okay, the internal energy. Internal energy, okay, from the first law of thermodynamics, kita tahu kan, okay, this one, first law of thermodynamics, okay, we have internal energy, one term is the heat transfer, internal heat, reversible, and another one is the internal work output or work input, okay. So these two relation comes from the first law of thermodynamics. Okay, delta Q minus delta W is equal to the change in internal energy. Okay, heat transfer and work. And okay, we have this heat transfer. Okay, this internal reversible heat transfer process can be written as equal to TDS. Okay, the change of the entropy. Okay, the entropy is the change of the heat over temperature. Okay, this is also another term to define heat transfer Q. Okay, we can write ds equals to delta Q over T, or delta Q equals to TDS. And the work output, the delta W work equals to PdV. This one we have seen in for first law. Example of ni apa tu? The compressible work. Example of the piston, okay. The work done by the piston, so depends on the pressure and the volume. Okay, this one we have seen, this one we have seen in for first law. Okay, the definition of work. This one QTDS, this is new. Okay, this is from first law, this is the second law. Okay, so come back to the these two form of equation of TDS. Okay, du PdV, or we can write it in kilogram per kilogram as small letter, or we call it as Gibbs equation, the TDS. Okay, and we have also the definition of enthalpy equals to U plus PV. Okay, U plus PV, enthalpy H equals to U plus PV, also from the first law. Okay, so if we derive derivation of H, so we have dH equals to du PdV. This is multiplication of derivation, so PdV plus VdP. Right, if we derive this equation, this equation, we have dH plus equals to du plus PdV plus VdP. And we also have this one, copy back, okay. we also have this one, TDS. Okay, so from both of these relation, we can conclude that TDS is also DH minus VDP. Okay, because DU DU plus PDV here, DU plus PDV here is equal to DH minus VDP. So DH minus VDP can also be written as DU plus PDV. Okay, I think I write on a whiteboard. Okay, just now we have this relation U plus PV. This is from first law, okay? And then, so if we derive derivation, make a derivation of this equation, okay? Derive, macam biasalah, okay? So, DH, this is DU, okay? And this one is multiplication, so we have to use P dV plus V dP. Okay, so we just derivation of this equation. Okay, somehow we also know that from the first relation, okay, that TDS, from the first relation of TDS equals to DU plus PDV. Okay, also we know this. Okay, so this actually comes from delta Q. Okay, delta Q. Okay, this is delta Q and this one is delta W. Where does this come from? From the first law, that DU equals to delta Q minus delta W. Okay, this is from the first law. This is also from the first law definition previously. Okay, so from this definition, we have this. Okay, jadi macam ni. Okay, from this, we have this. Okay, so this is the first relation of TDS. So now we are going to create the second relation of the TDS. Okay, so from both of these equation, okay, we see that this part and this part are the same. So we can write that TDS, okay, these are the same. So TDS is DH minus VDP. Okay, so this is the second relation of entropy TDS. So we have this first and second. First one, TDS equals to DU plus PDV. Second one, TDS equals to DH minus VDP. Okay? So that's how, okay, back to the these slides. So that's how we get these two relation. Okay? These two relation of entropy that we're going to use. Okay, so from these two relation, if we rearrange, we divide by T, temperature. Okay, divide all by T. We can also write it in this form. It's easier to see in this form because later on, if you want to integrate integral of the entropy, to calculate entropy, we integrate it. So it's easier this way. Okay, just divide by T, temperature. Okay, so we have du over T plus PdV over T. And also we have dH over T minus VdP over T. So this is the differential change in entropy in terms of other properties. Okay. Okay, everyone. Okay ke semua? Any questions so far? Okay, I just introduced the definition of entropy and the relation, the entropy relation that we're going to apply later on. Okay? So far semua okay?
Okay, Doctor.
Okay. Uh, Okay, this one, entropy change of liquids and solids. So we have, when we want to apply this entropy relation for liquid and solid and later on for gas. Okay, maybe for us in aerospace, we use a lot more entropy for gas. Okay, so, but I just explain this liquid and solid first, but we use a lot more the one for the gas. Okay, sebab aero, air. Okay, so this one for liquid and solid can be approximated as incompressible substance. So liquid and solid is we assume approximate them as incompressible, cannot be compressed. Okay, liquid and solid ni. Okay, apa tu opposite and then gas is compressible. That's why in aerodynamic, you guys learn aerodynamic 1, you guys only learn incompressible flow kan, incompressible flow. But for aerodynamic 2, you will see the one with compressible flow, more high speed gas flow. Okay. So this one, okay. So entropy apply to liquid and solid. Okay, so since we assume that liquid and solid is incompressible, means cannot be compressed, tak boleh ditekan atau boleh lah tekan, tapi dia susah kan. So it's hard, it's difficult to be compressed, this liquid and solid. Okay, so we assume that the change in volume of this liquid and solid are very, very small that we can neglect it. Okay, so that's why we said that dV, the change in volume of the liquid and solid, is nearly zero. It means we can neglect it. Okay, because since it is not compressible, so the volume won't change much. Okay, so that's how we can conclude this part. So if we assume that dV is zero because incompressible, so this part is already eliminated. Okay, so we have only ds equals to du over t, or we can also write u as c dt. C is the specific heat. Okay, specific heat. Specific heat also in kilojoule per kilogram per Kelvin. Okay, specific heat is per meter. Sometimes it is normally we will assume it as constant, but actually it changed slightly with temperature. It is a function of temperature, but for bachelor level, normally we will take a constant value. Okay, for example, for gas, the specific heat is for air 1005 or 1005 joule per kilogram per Kelvin. So for different types of substance have different value of a specific heat. So we can write this internal energy also du equals to c dt. Cp is at pressure constant or Cv as volume constant. So since both of these value for liquid and solid are nearly the same, so we can directly write it as C dt. Okay, specific heat, specific heat. So liquid and solid become, if we integrate this relation ds, so S2 minus S1, integrate and integrate this relation also. So we have C, function of temperature, dt over t. So if we assume that this specific heat is constant, so we can just write C average. So the integral of dt over t is ln t2 over t1. This is mathematics, you guys remember. Okay, so for isentropic process of an incompressible substance, we can isentropic. Okay, if this process is isentropic means no change in entropy. Okay, means S2 is equal to S1. So it's S1, S2 minus S1 is 0. Isentropic process. Isentropic process means no energy loss, no entropy, no change in entropy, not no entropy, no change in entropy. Okay, so for isentropic process like isothermal, isobar, isothermal is constant temperature, isobar constant pressure, isochoric constant volume. Okay, so we have this term isentropic means constant entropy. So constant entropy S2 equals to S1. So this relation will become 0. So what we can deduce from isentropic process of an incompressible substance, liquid and solid. So isentropic process means that the temperature also the same. T2 equals to T1 for isentropic process of an incompressible substance. Okay, this is what we can derive from the relation. Okay, this is more important for you. Entropy change of ideal gas. Ideal gas first, we assume the ideal gas. Okay, from the TDS relation just now, sikit cantik. Sikit. Okay. Okay, the TDS relation, we have this ds du over t plus pdv over t just now. Okay. Okay, so du this time around, we identify it as a specific heat at constant volume or specific heat at pressure, constant pressure. Cp constant pressure, Cv constant volume. Okay, so this time for gas, Cv and Cp, the value is slightly different. So we cannot just assimilate it as the same like solid and liquid just now. This one we assume it is the same, so we just write C, average. This one it is slightly different, so we need to write it properly, Cv, and this one we choose as Cp. Why we choose this one Cv? Because we have this volume differential. This one we have pressure differential, so that's why we choose Cp. Okay, so sorry. Okay, so du equals to Cv dt, the same relation as this one, just that we add the Cv. Okay, and from ideal gas, because this is ideal gas, remember chapter 2. Okay, chapter 2, I think we have learned this ideal gas relation. PV equals to RT, or we can also write it this way. Okay, but this is the ideal gas relation. PV equals to RT, ideal gas. So we can replace in the TDS relation. So du is Cv dt, du Cv dt, and this one, okay, we by using the ideal gas relation, P over T, we write it as R over V, so that we can use this V to integrate. Okay. Okay, I explain. Okay, we have the TDS relation. Okay, du over T plus PDV over T. Okay, the first relation. PDV over T. Okay, so we know that du is equals to Cv specific heat dt. Okay, this one we use specific heat at constant volume because we want to so that we can what to say we can use it apply it for dv volume, because we have volume here. Okay, so du this one du replace with a Cv dt. Okay, so that we can integrate this later on. Okay, this PT part, okay, from the ideal gas relation, since this is ideal gas, PV equals to RT, ideal gas, chapter 2 or chapter 3, cannot remember, chapter 3, okay. PV equals to RT, ideal gas, ideal gas. So here we have this PT relation with PT, P over T means R over V. Okay, from ideal gas. Okay, so we replace this part. So we have V. Nanti later on, it's easy for us to integrate because we want to integrate the equation later on. So CV. Now we have relation in terms of T. So we can integrate this part and also this one R dV volume over V. If we leave it here like this, also correct, but it's just that we cannot integrate, we cannot develop it more. Okay, so in order to integrate and develop it, we change it into this form from the ideal gas equation. Okay, so if we integrate this relation, so we have like just now, S2 minus S1. Okay, so this part CVT, so okay, CVT PT over T plus this one R dV over V. Okay, okay. All right, so if we assume this is constant also, so we have CV ln okay, ln T, okay, and to T2 over T1 plus R ln V2 over V1. If we integrate the function. Okay? So that's why, that's how we get this relation for ideal gas. Remember ideal gas only because we are using this part. So this is only valid for ideal gas. Okay. Okay, so we have this part relation. And we have this, we can also use the second TDS relation, which is this, relate with enthalpy minus VDP just now. So this enthalpy we can write as CPDT, the definition of enthalpy, also CPDT. So from the ideal gas relation, we write V, okay, ideal relation, ideal gas relation. Okay, this VT part can be replaced with R over P. Okay, from the ideal gas relation, R over P. So replace here R over P and replace here CPDT. So the same as this part. We write in integral form. So we have R ln P2 over P1. This is R ln V2 over V1. So we can use both of these relation. Depends on the parameter information that we have. If we have pressure, information on pressure, so we use this part, this relation. If we have information on the volume, so we use this relation. So both are valid. Okay. Okay, isentropic process of ideal gas, constant specific approximate analysis. Okay, so no. Okay. Okay, we're not finished yet. We can continue developing this equation to have other equation. Okay, setting this equation equal to 0, we get, okay, if the process is isentropic, okay, means that S2 equals to S1, so this relation is 0. Okay, isentropy, only isentropic process, okay, please remember, only isentropic process of ideal gas. So we have the relation that we had just now can be written, rearranged, okay, because this is 0. So we have this equation. Okay, okay, I try to show it to you. So S2 just now, the first relation that we have, S2 equals to S1, CV ln T2 over T1 plus R, the first relation that we get just now, which is this one. Okay, this one, right? Okay. So if isentropic process, so means that this is equals to 0, S2 equals to S1, isentropy means entropy constant. So we have this CV ln T2 over T1 equals to minus R ln V2 over V1. Okay, isentropy, only isentropic process. And then we can rearrange this one. Ln T2 over T1. Okay, we can write it this way. Ln V2 over V1. Okay, so R over CV here is power, right? Okay, because we have ln, so we can, like logarithm theorem, we can change it into power form. Okay, the RCV, and we can also write to eliminate the negative part. Okay, we can write it like this. Change the ratio V1 over V2, so we eliminate the negative, so R over CV. Okay. Okay, so ln, so becomes T2 over T1, T2 over T1, and V1 over V2. Okay, R over CV is what we call, okay, we have this relation. Okay, there's a lot of relation. It's okay, you don't have to memorize, just that you know R also can be written as CP minus CV. Okay, the gas constant R, CP over CV, and we also have this specific heat ratio, P gamma equals to CP over CV. Okay, so if you replace this relation in here, we have gamma of minus 1. Okay, R over CV here, we replace it by using this definition. Replace the R over CV with this relation, so we have gamma minus 1. Okay, why we need to why we cannot just state it as RCV? Because gamma of minus 1 is easier to calculate. Gamma is just a number. Normally for air is 1.4 or sometimes 1.2. So it's easier for us to calculate, okay, rather than if you use R over CV. Okay, so we have this relation, this first relation, okay, T2 of the ratio of T2 over T1 equals to V1 over V2, power of gamma minus 1. Okay, so that's how we get from here to here. Okay, even though you the steps, this is just to show you, to explain how we derive this part. Okay. Okay, so we have this one. So the same thing as this one. This one use the second relation of TDS just now. This one, okay, containing a P pressure. So the same method, we get this second relation. Okay, this is very important. These three relation are very important. For ideal gas, by using the ideal gas relation, we replace also P, this T with a volume. So these three relation, very, very important. We are going to use it several times until propulsion cost. This is valid for isentropic process, ideal gas. Please remember this one. Isentropic process, ideal gas. Only isentropic process, ideal gas. Why? Because we have we assume this zero. Okay, this is only valid for isentropic process because it otherwise, okay, we cannot become derive deduce until this step. Okay, so only isentropic process that we can use this relation because we assume this part is zero. And ideal gas, because we change the PVRT, we develop the equation by using the relation PVRT, so only valid for ideal gas. Okay, so again, remember these three form, very important. You're going to use it several times until proportion cost and until your future lah. Okay, so it's only valid for ideal gas, isentropic process, and constant specific heat. Okay, we assume constant. Okay, no, doesn't depend on temperature, etc. Constant specific heat. So the isentropic relation of ideal gas are valid for the isentropic process of ideal gas only. Okay, so this is the same part. You can write it this part or this way or this way. So but you always use this method, this type. Okay, relation T2 over T1, P2 over P1, V1 over V2. Okay, very, very important. Okay. Okay. Okay, so far?
Okay, Doktor.
Okay, ingat ni je. Okay. Dia penat. Okay. Reversible steady flow work. Okay. Okay, banyak pula. Okay. Okay, this is go back to the first law of thermodynamics. Okay, we now we mix the first law and second law. Okay, first law, remember we have the delta Q minus delta W dH plus the kinetic energy and potential energy. Okay, so the Q is TdS, so this one we already have just now. Okay, okay, so okay, we can rearrange this first law equation, TdS dH minus VdP. Okay, the second TdS relation. Okay, so from both of these, we have delta Q equals dH minus VdP. But this one, this part the same, ni sama. This is the same, so delta Q equals to dH minus VdP. Okay, and if we replace this part here, okay, dH and delta Q, so we have minus VdP here. Okay, so that's how we get, okay, apa saya tunjuk. Okay, we have this second TdS relation just now, TdS dH minus VdP, the second relation just now. Okay, TdS. Okay, and this part, this is delta Q. Okay, delta Q. So we have delta Q equals to dH minus VdP. Okay. And then from the first law relation, we have delta Q minus delta W equals to dH plus kinetic, the change in kinetic energy and the change in potential energy, right? Okay, so this dH, okay, delta Q minus dH is VdP minus VdP. Okay, so from here we can masukkan VdP. So that's why we get delta W VdP minus DKE minus DPE. We change the negative positive. Okay, so that's how we get this one. Okay, for reversible steady flow work. This is to apply in steady flow, for example, compressor, turbine, nozzle. Okay, reversible steady flow. Okay, so we have this part, this one, reversible steady flow. So if we integrate it, okay, we assume that no kinetic energy and no potential energy or very small potential energy. Okay, so when kinetic and potential energies are negligible, so we have only this reversible work, VDP. Okay, otherwise the full equation is like this. Okay, reversible steady flow work. To calculate reversible steady flow work. Okay, for the steady flow of a liquid through a device that involves no work interaction, such as a pipe section, the work term is zero. If we for liquid steady flow work for liquid device, for example, pipe. Okay, for pipe there is no work done. Pipe kan, I like the only the flow, fluid flow, so no work. Okay, so no interaction. So this part and no work interaction. So this part is zero, no work. Okay, so this relation will become the Bernoulli equation that you use in aerodynamics, fluid mechanics. Okay, from this reversible steady flow work, we get the Bernoulli equation because for pipe, right? For pipe in fluid mechanics, you use Bernoulli equation, right? So that's how we get this Bernoulli equation. Okay, no work because pipe has no work interaction. So this one, this is kinetic energy, and this one is the potential energy. So we get the Bernoulli equation from the reversible steady flow work. So you relates the thermodynamics part with fluid mechanics. Okay, Bernoulli equation. Okay, so there are three forms to write the reversible work in terms of kilogram, etc. So tak apa okay, this one. Okay, so steady flow system, okay, with no kinetic energy and no potential energy, so only reversible work, the integration of VDP minus VDP. Okay, for closed system, okay, for closed system, we can just this closed system that we have seen earlier, previously in previous chapter, for piston. Piston is a closed system, piston engine. So the reversible work is PDV directly, right? Okay, this is in the previous chapter. But here for steady flow system, this is the new part. This is previous chapter. This is in this chapter. Okay, steady flow system, the reversible work is negative VDP. Okay, reversible work relation for steady flow and closed flow system. So they are different. Okay, steady flow system like this. Reversible work is like this. Okay, how do we get like this way? From here. Okay. And for closed system, this one we have seen previously, previous chapter, the reversible work of a piston. Okay, the closed system is PDV. Okay. So if there is no change in volume, means there is no work. Okay, for closed system. But here it is different, depends on the pressure. Okay, so that is reversible steady flow work. Okay, so example of application, turbine. Okay, you can see this application of reversible work in turbine. Okay, rearrange the equation, etc. So you have this proof that steady flow device deliver the most and consume the least work when the process is reversible. Of course, reversible is ideal process. So if you have a reversible process, it will deliver most work means more power output, okay, and consume the least work. This is just to show from the equation to show that the reversible process work is higher than the actual reality work produced. Okay, for example, for a turbine. Okay, this is compressor. Okay, but before we continue, I think we take a break. 15 minutes. Less 13 minutes. Until 10:45. Okay, we take a break until 10:45. 13 minit, 13 minutes. Take a break. Before we continue. Okay, we continue. 10:46. Okay, you guys there? Afiq, Miza,
Yes, sir.
Akmal, Omar, Umi, Tenshan, Katikan. Okay, we continue. Okay. So we are only at the 10 slide. I have actually only 26 slides, less than the previous chapter, but it takes longer to explain each slide. Okay. Anyway, okay, just now we see turbine. Okay, application of reversible steady flow work. Okay, using the first law and second law for turbine example. So this one is for compressor. Okay, compressor. Okay. Sekejap Reversible. Okay, so the reversible steady flow work for compressor. Okay, we have this relation. Okay, just now we have this one example. Okay, this one example general equation which can be applied for turbine. Okay, for compressor is the same. It's just that here we don't have the negative value anymore because compressor is the function is opposite of turbine. So if so for example for turbine the pressure at the exit is less than the pressure at the inlet because in the turbine we expand, decrease the pressure. So in the compressor is the opposite. We compress, so we increase pressure. So that's why the change in the negative positive. Okay, just that about the increasing pressure or decreasing pressure value. Okay, so for if the potential and kinetic energy is are negligible, so we have this form reversible work for compressor. So for okay, we have isentropic, polytropic, and isothermal. So I think we only focus on this part, isentropic, which is more frequently used, and the isothermal. Polytropic we seldom use, so you just can forget it. Okay, okay, isentropic. So for isentropic process, okay, we have the this PVK relation K or gamma just now, the gamma just now, the specific heat ratio. So it can be written, the reversible work, okay, can be written this in this form. Okay, gamma RT over gamma minus 1, P2, P1, okay. So this is for the isentropic process, or we can also write for isothermal process, the compressible work. Okay, we just replace the V using the ideal gas relation, and P integrate ln P2 over P1. This is more frequently used that we use. Okay. Okay, it's okay, this one, okay. So this is the example of PV diagram of isotropic, polytropic, and thermal compression. Okay, so you just, I think you just need to know this one and this one relation that we are going to apply. So that is for compressor, okay? The compressor work. Just now, this one is the work for turbine. This is for compressor. Okay. Some compressor have extra component that we add to the beside the compressor, okay, which is intercooling. Okay, intercooling is one type of heat exchanger. I think you have heard about this before, intercooling. Okay, so for example, turbine we add reheat. Okay, we heat again, heat the fluid air inside the turbine before the turbine, so increase the temperature. So for compressor, some engine they have intercooler, and intercooler. Example, in your vehicle, your car, sometimes we have intercooler. Okay, so this, what is the function of this intercooling? So intercooling, it helps to save work, kind of like save work. So if you minimize the work in the compressor, so it's better in terms of efficiency. If we can minimize the work that we need to input in the compressor, okay, so we have a more efficient engine. Okay, so one method, one way to minimize this compression work, to save this compression work, is by adding an extra heat exchanger which is named intercooler. Okay, intercooler beside the compressor. Okay, so it can minimize the compression work. To minimize the compression work during two-stage compression, the pressure ratio across each stage of the compressor must be the same. Okay, tak apa. Okay, just that want to explain that we add this intercooling part for multi-stage compression, means that higher low compression and then higher compressor, right? Okay, so between these two compression, high and lower compression process, we add an intercooling. Okay, it can helps to minimize the compressor work. For example, okay, you look at this. Okay, before that, okay, okay, just to explain, okay, heat exchanger, okay, we see is a device, okay, for heat transfer process kan. Okay, so heat exchanger has many types, depends on the function, okay, the objective. Okay, so as long as the device is to the function is to exchange heat, we call it as heat exchanger. So heat exchanger has different types. One is intercooling, so the function is to cool, okay, to intercool. So intercooler. We have evaporator or boiler, okay, have we seen earlier, evaporator or boiler. Evaporator is for gas, boiler is for liquid. And then we have condenser, okay, to exchange with the water cooling heat sink. Remember last week we see heat sink. So condenser exchange heat with the heat sink. Evaporator or boiler exchange heat with the heat source. Include here also, evaporator boiler is the combustion chamber. Combustion chamber also the same function as evaporator boiler. We also have reheat, okay, to increase this is to cool down, this is to increase temperature. What else? We will also have regenerator, okay, regenerator to exchange heat from the hot side to the cold side. As I've explained to Marwan last week, okay, regenerator. So all of these are types of heat exchanger, okay? Just want you to understand this concept. All of them are heat exchanger, just that different in the function objective. Intercooler is to increase, to lower down the temperature. This is to evaporate, to boil, okay, to increase heat input, okay, condenser exchange heat with the heat sink, reheat to increase temperature, regenerator to exchange heat from the to regenerate the heat from the hot side to the cold side. So all of them needs exchange of heat in the device, exchange of heat in the device. So that's why they are what we call heat exchanger. Okay, so intercooler normally is added at the compressor, between compressor or before compressor, okay, to save the work used in the compressor. Okay, because of course if we can save the work use input, the work that we need to input in the compressor, we minimize the work, so we can increase the efficiency. means that we use less electricity, etc. Because to compressor, we need to input work, electric work, etc. So if we can minimize this work, we increase the efficiency of the engine. Okay, so this is the TS diagram, temperature versus entropy diagram, to explain, to show to you how this intercooling process helps to reduce the work in the compressor. Okay, for example, we have multi-stage, means that we have at least twice compression process, low compressor and high compressor, two stage. So instead of if we don't have this intercooling part, this PX pressure, this intermediate pressure, if we don't have this intercooling, means we only have a compressor. Okay, we need to compress the fluid from state 1 to state 2. Okay, means that state 1 to state 2 directly like this. Okay, we need to increase the pressure from P1 to P2. So without the intercooling, the fluid will be increased from state 1 to state 2 here. Okay, the pressure is still the same with or without the intercooling. With or without the intercooler, the pressure P1 and P2 are the same. The one that change is the temperature. Okay, if we don't have intercooler, the temperature will be at this point, which is higher than the temperature here with intercooler. So if the temperature is higher, means that we need extra work, okay, to increase the fluid to this temperature. Okay, but otherwise, if we add intercooling, okay, the function of intercooling, it can intercool, cool back the fluid, cool back the fluid and recompress again, so to a lower value of temperature. Okay, I show you example. Okay, if I describe here the TS diagram of a compressor. Okay, macam ni kan. Sorry. Macam mana tak? Okay, kurang lah. Okay, like this. Okay, if we don't have intercooler, this is 0.1. Okay, so this is P2, the isobar line, this is P1. Okay, we need to compressor, we need to compress, increase pressure of the fluid, the working fluid. Okay, if we don't have intercooler, so the fluid should be straight line. The fluid will be increased from state 1 to state 2 at this point. Okay, without intercooler, directly this point. Okay, increase. So this will be the total work input in the compressor that we need to give. Means we need to use work to give work input. Okay, without intercooler, directly. So temperature T2 here, this is T2 and this is T1. Okay, but if we add intercooler, we intercool first, okay, lower down and increase back, compress again the fluid. So at 0.2 prime, for example. Okay, so this the pressure is still the same. P2 is equal to P2 prime. Okay, but we still reach the final point, the same final pressure, but the temperature will be different. Okay, will be lower. Means that the work input here, because work the work depends on the temperature that we put, the change in the temperature. Okay, so T2 is less, so means that the work input is lower. So that's why we save this one. Okay, work input is lower, so that's why we save work. Okay, by adding the compressor, the intercooler. Okay. Okay, that is the function. The function of intercooler. We intercool at constant pressure. Intercool at constant pressure. Okay, normally all the process in the heat exchanger, intercooler, evaporator, reheater, regenerator just now. Okay, the ideal process is at constant pressure. Okay, so we assume constant pressure, and then we compress back. So we use less work, okay, by adding intercooler between the compressor, okay, between the stage, the compression process stage. Okay, that is the function of intercooler. Okay, now you know the function of intercooler, right, in your car or in the engine. Okay, then turbine, isentropic efficiency of turbine and electron compressor. Okay. Compressor work, minimizing compressor work. Okay, isentropic efficiency of steady flow device. Okay, from the isentropic process. Okay, there's no reversibility and serve as the ideal process for adiabatic device. Okay, so ideal process, we assume it as isentropy. Isentropy is an ideal process, means no irreversibility. Okay, no energy loss. Okay, so ideal process reversible. Okay, so actual process is irreversible. So to quantify for turbine efficiency, this is turbine efficiency. Okay, so efficiency is the ratio of actual turbine work over isentropic turbine work. Okay, ideal. Actual over ideal. Okay, so we have the efficiency of a turbine, isentropic efficiency of a turbine. Okay, actual over ideal. Okay, of course. So the efficiency has to be less than 1 lah, less than 100%. Okay, this is the HS diagram, the same as TS diagram. Okay, so turbine, remember again, the function of a turbine is to decrease expand, so you decrease pressure. So, so for actual process, okay, actual process, the exit pressure is the same. Okay, we still reach the same exit pressure, okay, P2, but the total energy H, okay, total energy use is less, okay, for in actual process. But for ideal process, isentropic process, if you have no loss, okay, total energy, total exit energy is lower, H2S. Okay, this is higher, H2A. The level of enthalpy is higher. Okay, so so this is the different process, actual and isentropic. So that's how we get the efficiency of a turbine. Okay, H1 minus H2A, the enthalpy, H1 minus H2A over H1 minus H2S. If you don't remember this ratio, just remember that efficiency cannot be higher than 1. So the value, the one that is lower will be at the top, and the one which is higher, the difference is higher, the change is higher, will be at the bottom, lower. Okay, if you don't remember the ratio, you just think about that the efficiency cannot be higher than 1. Okay, so you just rearrange the position of the ratio. Because for compressor, the ratio is the opposite. Okay, we put the isentropic compressor work first at the top over the bottom, lower actual compressor work. Okay, because efficiency cannot be higher than 1. Okay, cannot be higher than 100%. So isentropic from 1.1 to 0.2S, this is lower, the change is lower, the work done is lower. Okay, then the actual process, the work done is higher. Okay, the work input in the compressor is higher in the actual process. Okay, so so this is will have a higher enthalpy change. Okay, from this graphic, it's easier to see from the graphic. So that's why I advise you to sketch the process in a TS diagram, etc., so that you can see clearly the difference of the process, and it helps you to calculate. So compressor efficiency. This time around, the isentropic, the ideal process will be at the top, okay, and the actual process will be at the bottom, okay, because the actual process means the work input to the compressor will be higher. Of course, if you think it logically, okay, actual process reality with the friction, etc., of course, you need to put extra work to the compressor due to the friction. You want to overcome the friction. You want to overcome all the circumstances. So to overcome all this, you need to put extra work. So that is what actual process that actually occur in the actual process. So that's why actual process is higher. You need to put extra work to the compressor. But isentropic is the ideal process where we assume no friction, no loss, everything is normal, okay, everything is in arrange, organized, okay. So it will be lower, less work needed to put to the compressor. Okay, if you want to think logically like that. Okay, so that's why isentropic process ideal is lower. Okay, so you can write the efficiency of the compressor in this form. Okay, this one, okay, if you want to change it for a pump, so compressor and pump, the function is the same, is to increase the pressure to compress. Instead, that compressor is used for gas. Okay, again, I repeat, compressor is used for gas, pump is used for liquid. Okay, so for pump, we can write it this way. But it's still the same, isentropic over actual, just that we change the parameter here. Okay, so this is how the steady flow work in the compressor, the HS diagram. Tak apa, okay, this one. Okay, and then the last one, efficiency, is for nozzle. Okay, so you have efficiency for turbine, efficiency for compressor, and efficiency for nozzle. Nozzle, very important for high-speed gas flow. For power plant, we don't use nozzle normally. For power plant, we don't use nozzle. But for high-speed gas flow, which is for aerospace, jet engine, we need nozzle to increase the velocity, to increase the kinetic energy, because we want to achieve the high speed. Okay, so we need nozzle. So nozzle, for nozzle, the process is kind of like the same as turbine. We decrease the pressure in the nozzle, but in the nozzle, the most important part is the kinetic energy. Okay, so even though it's still the process is decreasing, the pressure is decreasing, but we focus on the energy because of the speed, the velocity of the fluid in the nozzle. That is more important. Okay, so from velocity, actual kinetic energy over the isentropic, the ideal process kinetic energy at the nozzle exit. Okay, so this is how do we write the isentropic efficiency. So it is based on the velocity. Okay, this time around not based on the work, because no work done or no work output in the nozzle, but we have kinetic energy. Okay, if the inlet velocity of the fluid is more relative to the exit velocity, the energy balance is, okay, we can write this way. Okay, so this is the nozzle efficiency of an adiabatic nozzle. Okay, so we have these three equation for isentropic efficiency of steady flow device. Mean you have inlet, outlet flowing in the device. Turbine, this is turbine. This is compressor, efficiency of the compressor, and this is efficiency of nozzle. Okay, remember nozzle, you use velocity. Compressor and turbine, you use the calculation of work, because we use work to run the turbine and compressor. Okay, Okay, back to our entropy stuff. Okay. Okay, entropy balance. Okay, before this, we first law we have energy balance. So second law we have entropy balance. So how do we write this entropy balance? Okay, entropy balance. The definition is the total entropy entering minus the total entropy leaving exit. Initial minus exit plus this is the different part, total entropy generated. Okay, the irreversibility generated, okay, equals to the change in the total entropy of the system. Okay, so not just S in minus S out, but we have this entropy generated in the closed system. Okay, okay, first law we have energy balance. Energy balance of the first law, the change in energy of the system is only energy in minus energy out. But for entropy, the change in entropy is S in minus S out plus the generated, the entropy generated, the level of the disorder of the molecule, level of the disorganized of the energy to molecule. Okay, that's how the entropy is generated. So we have to take into consideration in the entropy balance form. Okay, so yes, S final minus S initial plus the S generated, okay, of the system. Okay, if there is no entropy generated, so only system S2 minus S1 lah. Okay. Okay, mechanism of entropy transfer S in and S out. Okay, just now we have ds equals to delta Q, or TDS equal to delta Q over T, kan? TDS equals to delta Q over T, so we can integrate that form. So we have this relation, okay, TDS just now delta Q over T, so we integrate it. So this is how we define the entropy transfer by heat. So entropy can be transferred by heat, okay. So if we heat up the gas, okay, the velocity of the molecule of the gas will change. So there is entropy generated, okay, within the gas. Entropy generation is this one, entropy generation by friction. There is no entropy transfer by work, okay. You cannot transfer induce generated the entropy by work, but you can generate the entropy via friction, okay. So that friction will become heat, okay. So heat transfer is always accompanied by entropy transfer in the amount of Q over T, where T is the boundary temperature. Okay, T here, T ni boundary temperature. Okay, for example here, TB boundary temperature is 400 Kelvin. So Q, the heat transfer to the system 500 kilojoule. So the total entropy transfer is 1.25 kilojoule per Kelvin. Okay, no entropy accompanies work as it cross the system boundary. Okay, because work is from the, for example, work from the shaft crossing the boundary. So no entropy work. But entropy may be generated with the system as work is dissipated into a less useful form of energy. So it is dissipated in terms of friction. Okay, so it's transferred by heat. Okay, entropy transfer by mass. Okay, entropy transfer by mass. So the a change in the mass within the control volume will generate change in entropy. Mass contains entropy as well as energy, and thus mass flow into or out of system is always accompanied by energy and entropy transfer. Remember, energy, first law, okay, energy can be transferred by heat and by mass. So the same as for entropy, entropy also can be transferred by heat and mass. Okay. Sorry. Energy can be transferred by work and mass. Okay. Entropy by heat and mass. Okay. Okay, I write here. Okay. And energy first law we have seen in chapter 5 before the first law of the thermodynamics. So energy is transferred by work and mass. So that's why you have the work, etc. in the your energy balance. Entropy, it is transferred by heat and mass. Okay. Okay. Remember this one. Okay. Let's check. Energy transfer by work, heat. Okay. Work, and mass. Okay. Okay. So you have the energy, the entropy transfer by mass. Okay, so the entropy generation, okay, the same equation just now, net entropy transfer by heat and mass. So this is S in and S out is net entropy transfer by heat and mass. This one entropy generation, generated, so the total is the change in entropy. Okay, so you can also write in terms of rate of energy, net entropy, rate of change in entropy. So either one, in terms of kilojoule or in terms of kilowatt. Okay, okay, closed system. So we have the entropy change for a closed system. Okay, so for a closed system, the change in entropy, okay, or the entropy change of a closed system during a process is equal to the sum of the net entropy transfer through the system boundary by heat transfer and the generated within the system boundary. Okay, so for a closed system, okay, the change is only between S2, the initial point, minus the exit minus the inlet. Okay, the final point minus the initial point. That is for closed system. Okay. Control volume. Okay. This one, if for control volume, inlet where you have open system like this, okay, open system like the compressor, turbine, nozzle just now. So means that you have a change in mass, okay, because closed system you don't have change in mass, no flowing in and flowing out of the mass. So you only have entropy in terms of heat. Okay, but for open system or steady flow system, you have also to include the change in entropy, entropy transfer by mass. Okay, because you have some amount of mass flowing in and out through the control volume. Okay, the turbine, compressor, okay, or the steady flow device, pipe. Okay, heat exchanger included also. So so that is so this is the how do we write the entropy generation for steady flow single stream, steady flow single stream adiabatic. Okay. Okay, the entropy of a control volume change as a result of mass flow as well as heat transfer. Okay, the change this one. Okay, the different part is this one. Okay, you include the change in entropy. This one is without the mass. This one is with the mass. Okay, you can write with either in kilojoule or kilowatt. This is an example of entropy balance for heat transfer through a wall conduction. We have a conduction process. So we can write the entropy balance equation this way. Okay, no transfer of mass. Okay, no transfer of mass between the brick wall here. So you only have entropy balance in terms of entropy exchange transfer by heat. Okay, this one in a throttling process in a pipe, for example, in pipe you have change in mass, so you need to include the entropy change by mass, but you don't have the change in entropy by heat. So that's why you don't have heat here, only change by mass. So example, throttling for pipe, you have this one, and for wall you only have heat. Okay, example lagi tak apa. Okay. Okay, finish. Alhamdulillah at last. Okay, 11 nearly 11:30, 11:21. So we have time to do maybe I have 4 examples question, but maybe you can do 1 or 2. Okay, we have time to do 1 or 2 exercise example. Okay. Okay, maybe 1 minute. Okay, we need to calculate electricity a bit. Okay, try to read first the question, example. Okay, later on we do the exercise. Okay, a cryogenic manufacturing facility handles liquid methane at 115 Kelvin. Later on, I have the this table for you. Okay, liquid methane at 115 Kelvin and 5 megapascal. Okay, at a rate of 0.28 meter cube per second. Okay, the mass flow rate, this time is a volume flow rate of the liquid the liquid methane. Okay. Okay, before that, what is cryogenic? Maybe some of you have heard this process, but maybe this is a new word for you. So cryogenic is actually a production process of materials at very, very low temperature. Okay, so if you look at it, 150 Kelvin, Kelvin equals to how much degree Celsius? Cik je kan? 115 negative 158. Negative 160 degrees Celsius. So very, very at low temperature. So cryogenic manufacturing is a process to manufacture, to produce materials at very low temperature. So that's why here we use methane. Okay. So that is cryogenic. So at 115 Kelvin and 5 megapascal, a rate of volume rate 0.28 meter cube per second. A process requires dropping the pressure. A process requires dropping the pressure of liquid methane to 1 megapascal, which is done by throttling the liquid methane by passing it through a flow resistance such as a valve. Okay. Okay, so in order to manufacture, to conduct the cryogenic manufacturing, means in order to manufacture this, we need to decrease the pressure of the methane from 5 megapascal to 1 megapascal. Okay, so that's what it means. This process requires dropping the pressure. This process requires expansion, decreasing of the pressure of the liquid to 1 megapascal, which is done. How do we do this? Is by throttling the liquid methane. Okay, throttling is like throttling device like a pipe. Okay, by passing it through a flow resistance such as a valve. Okay, so here we use a throttling device. A recently hired engineer proposed to replace the throttling valve by a turbine. Okay, now we use a turbine. Okay, instead of using the throttling valve like a pipe, we use a turbine in order to produce power while dropping the pressure to 1 megapascal. So instead of if we use the throttling valve like a pipe, we only can reduce the pressure without any extra power produced. So rugilah kan, we don't have any benefit to that. Okay, so instead we replace the valve with a turbine. So other than reducing the pressure, we can produce power if you use a turbine. Okay, so determine the maximum amount of power that can be produced by such a turbine. Okay, how much power this turbine can produce while decreasing the pressure. Also determine how much this turbine will save the facility from electricity usage cost per year if the turbine operates continuously 8,760 hours per year and the facility pays 0.075 cents per kilowatt hour for electricity. So you need to calculate a bit of electricity a bit. Okay, so but first part, maximum amount of power that can be produced by such a turbine. Okay, so we have our initial point 5 megapascal and 115 Kelvin. Okay, Okay, so if we look at this table, the properties of liquid methane, okay, at 115 Kelvin and 5 megapascal. Okay, so this one, 110 Kelvin, 5 megapascal, we have entropy. For 120 Kelvin, 5 megapascal, you have this enthalpy and entropy. Okay, so you take since we are going to use, we need the value at 115 Kelvin. So we just average it at the middle point between 215 and this one around 250. Okay, so we get around 230 maybe. 15, okay, you calculate just the middle point of this, both of these. So you get around 232 enthalpy and this one entropy. Okay, between both of these values, so 4.9 something. Okay, the middle point of this average point of this 4.8 and 5.1, so you get around 4.99 or 5. And then the density also, density 429 and 415, so you get around 422, the middle point, the average between those two. So because we need the one at 115 Kelvin and 5 megapascal. And at state 2, at the final state, we need to reduce the pressure of the methane to 1 megapascal. So means that P2 is 1 megapascal. Okay, P2 is 1 megapascal. And we assume that the process is isentropic. Okay, isentropic flow. Okay, so S2, the entropy final is the same as S1. So no need to find it. Okay, but H2 at 1 megapascal. Okay, at 1 megapascal between 1 megapascal here and 1 megapascal here. So between 209 and 244, the middle. So you get around 222. 222 kilojoule per kilogram because at 115 Kelvin. Okay, at constant temperature, constant pressure, constant entropy. Okay, for turbine. So you get so you get 422. Okay, tulis lah. Okay, just now state 1. State 1, you have P1, 5 megapascal. You have this information given. And you have T1, 115 Kelvin. Okay, so from this information, you look at the properties table of liquid methane. So you have H1, 232 kilojoule per kilogram from the table. and you get S1 around 4.99 or 5 kilojoule. Don't forget the unit, kilojoule per kilogram per Kelvin, and density in case you need it around 422. Density kilogram per second. Density kilogram per meter cube. Okay, and then at state 2, final state, we need to decrease the pressure to 1 megapascal. Okay, when we assume this is we are in steady flow process, isentropy, etc. We are in this chapter, so we assume S2 equals to S1, isentropic process. Okay, and at same level of temperature. Okay, so you have H2 from the table also. You have H2 222 or 223 kilojoule per kilogram at 1 megapascal and 115 Kelvin. If you assume that the process is isothermal, so constant temperature. Okay, what do we want just now? Apa yang kita tengok tadi? Determine the maximum amount of power that can be produced by such a turbine. Okay, we want to calculate the power, maximum amount of power. Now we have the enthalpy, kilojoule per kilogram. Okay, so to change it into power, we need to handle the mass flow rate. Okay, mass flow rate. So mass flow rate, we have density from the table, and we have the volumetric rate just now 0.28 given. This one 0.28, and the density. So we multiply it, we get 118.2 kilogram per second. So that is our mass flow rate of the metal. Okay. Okay, so in order to calculate the amount of power, maximum power that can be produced by such a turbine. Okay, so from the energy balance, we have E in equals to E out, energy balance. So we don't have Q, heat transfer during the process, no heat transfer during the process. For turbine, we don't have heat transfer, we only have work. Okay, so the work output from the first law, energy balance, the work output is only consider the enthalpy. Enthalpy H in H1 minus H2, because we want to have a positive point, so H1 is higher, more energy. So that's how we get power, the maximum amount of power produced by the turbine. So this mass flow rate, H1, H2, mass flow rate. So you get the output power of a turbine around 1123 kilowatt. Okay, we use kilowatt because we have the mass flow rate in seconds. Okay, so this is from the energy balance, first law, energy balance, because turbine, no heat transfer. Okay, for turbine, look back at the theory in the chapter, no heat transfer within the turbine, only heat input output. And then no kinetic energy, we neglect the kinetic energy and we neglect the potential energy. Okay, so only enthalpy, the change in energy transfer by mass. So only the enthalpy part. Okay, and the work, of course, work output. No heat, no kinetic energy, no potential energy. So we have this equation, this energy balance. First law, work output, work net output is the energy transfer by mass, which is enthalpy. Okay, so you can calculate directly the amount of power output. Okay, 1,123 kilowatt. And then what do we need? Also determine how much this turbine will save the facility from electricity usage cost per year if the turbine operates continuously 8,760 hours per year. So 8,007 the power plant is operated during a year annually at 8,760 hours. So the total annual power production, okay, just now we have W output, net output, W net output 23 kilowatt, okay, or kilojoule per second, and this is kilojoule per second. So we need to change the second in a year. Okay, we can change a kilowatt. So annual power production is the W out times the hour, okay, the hour 8760 hour per year. So we have this value, okay, in terms of kilowatt hour per year. Okay, this is in kilowatt and this is in hour per year. Okay, so you have the answer in kilowatt hour per year. Okay, that is annual power. How much does one receive the facility from electricity usage cost per year if the turbine operates continuously, and the facility pays kilowatt for you. Okay, so how much we pay? Annual power saving. Annual saving by using the turbine. So the power production here, the annual power production multiply with the unit cost power 0.075 kilowatt hour per year. Per kilowatt hour, sorry, per kilowatt hour. Okay, this is per dollar per kilowatt hour. This is kilowatt hour per year. So you have the answer in dollar per year. Okay, how much you pay per year? How much you save actually per year? Okay, by using the turbine instead of the throttling device. So you calculate around 700,000. Okay, the annual saving. You can save per year around $700,000 per year by replacing the turbine. So because you can produce electricity from the turbine, not only decrease the pressure. Okay, so that is the answer. Okay, you calculate by yourself. Okay, determine how much this turbine receive the facility from electricity usage cost per year if the turbine operates continuously hour per year and the facility pays for electricity. Okay. Okay, 1 minute for you to digest. Any questions? Okay. We continue to the next questions regarding compressor. Okay, this time around we're going to see example for a compressor. Uh, More short, simple. Okay, compressor work. Determine the compressor work input required to compress steam isentropically. So this time around we directly assume it's isentropic from 100 kilopascal to 1 megapascal. Okay, so we compress, increase pressure 100 kilopascal to 1 megapascal. Assuming that the steam exists as saturated liquid, A as saturated liquid and B saturated vapor at the inlet state. Okay, so the first one is liquid. So saturated liquid, okay. And the second one is vapor. Okay, so remember the slightly difference of a reversible work equation for liquid and vapor. So we do the liquid first. Okay, saturated liquid. So for liquid, liquid just now. Irreversible work, okay. For compressor, okay, we can use this one. Integral of VdP. Okay, okay, we want to calculate the reversible work. Integral of 2 over 1 VdP. Okay. So here we need to find the value of V. Okay, we can assume that V here, V is constant. So we can take out from the integral. So we get V P2 minus P1. Okay, P2 and P1 we have the information, just that we have to search for information for V. Why we can assume it as constant? Actually, okay, like just now, for liquid, the change in the volume during compression process is very, very small. That actually you can neglect it, but here we don't totally neglect it. Since that we assume that the uh, the change is very small, so the volume maintain at the same volume. Sorry, tak tunjuk ni. Okay, so we write it this way. So we can assume that the volume of the liquid, because during the compression, the change in the volume of the liquid is very, very small. So means that the initial volume is the same as the final volume. So we only search for one value of volume. So we can integrate this way. We can take out the volume and integrate only the pressure part. Okay, because liquid, this is liquid. Liquid is incompressible substance. Remember, liquid and solid is incompressible. So the change in volume is very, very small. So that's why we can say that V1 is equals to V2. So we only change for V liquid. Okay, VF. In the table is VF. Okay. So look at the table table A5 that we have previously in previous chapter. So we can use that table A5 at 100 kilopascal. Okay, we take the initial value of pressure 100 kilopascal, because at that point the substance is in liquid form that we want to consider as constant. So from the table A5, we look at the table A5 that we have before this. Okay, so we take a VF, and here is very small, 0.001043 meter cube per kilogram. Okay, and then we replace this value inside here. Okay, this one is 1 megapascal. 1 megapascal just now, 1 megapascal. Okay, 1 megapascal means 100 kilopascal. 1000 kilopascal. And this one is 100 kilopascal. Okay, 1 megapascal is 1000 kilopascal. Okay, this one is 100 kilopascal. So you have the volume and you have the pressure. So you get the reversible work, okay, in the compressor, 0.94 kilojoule per kilogram. Okay, so for liquid is simple. So the amount of work, compressible work, to compress the saturated liquid is 0.94. Okay, directly from the equation. Second one, if we assume that the steam is in saturated vapor. Okay, it is a saturated vapor at the inlet state. So this time around, so we use the equation TdS equals to dH minus VdP. Okay, the TdS relation. So here the process, they tell you that the process is isentropic. So this one 0. Okay, isentropic, this one 0. So you have VdP, which is the work, equals to dH. Okay, so back to the relation, the same relation of compressible work, VdP. So means that we can calculate it by using dH, which is, if we integrate it, H2 minus H1. Okay? Okay, so easy. Okay, so you have for saturated vapor, this relation. So just find the H2 and H1 using the table A5, A6, etc. So P1 for at state 1, P1 is 100 kilopascal just now. So saturated vapor, so look at the table A5, saturated vapor, for saturated vapor. So you have H1 and S1. But you're only going to use H1. So H1 2675 from the table. 2675, okay. And for state 2, P2 is at 1 megapascal. So H2 from the table. H2 3195 kilojoule per kilogram. Okay. This is saturated vapor. Saturated vapor, we have this relation. We can use table A5 and table A6. Okay, this is at initial point. Initially, it was at a saturated vapor states phase, and finally, it will become a dry vapor, dry air. Okay, so the final state H2 at 1 megapascal when we have compressed the fluid. Okay, so we get 3194. Okay, now that the steam has become superheated, okay, this is superheated because we have compressed and heat up the fluid. Okay, the steam. This is saturated vapor. Earlier it was at saturated vapor phase. Now it has become superheated because we increase the pressure and temperature, we compress it. So we look at the superheated vapor at 1 megapascal. So we have H2. So now replace H2 and H1 inside here. So you get the reversible work around 520 kilojoule per kilogram. Okay. So you see the compressible work, the compressed work, for liquid is very, very small, only 0.94. But for gas, okay, we need to put extra work, which is 520 kilojoule per kilogram. Okay, so compressing a steam in the vapor phase form would require around 500 times more work than compressing a liquid. Okay, between the same pressure limit P2 to P1. Okay, so liquid you only need around 1 kilojoule per kilogram. This one you need around 500 kilojoule per kilogram for gas, vapor. Okay. Any questions? Understand? You use this. We use the old table that we already have, table A5 and table A6. Table A5, the vapor, and then the superheated water steam table. Okay, by looking at the pressure. Okay, we finish here. Example 3 and 4 you can try. Otherwise we if you have time next week, and we have 2 weeks more. Next week I will start another chapter, the final chapter concerning gas power cycle, the most important part for your aircraft engine, gas power cycle. And if we have, inshallah, we have time, maybe the last final week 14, to do some revision. So I'll try to compile all the exercise example. So we try to do more, look at more example before your final exam. So only left with one chapter, gas power cycle, but it's the most important. So okay. Okay, if no questions, so we stop here for today. Okay, that's soalan. Try to digest it. I know it's a bit full for you, but try to look at the example. Again, because if you just read the theory, maybe you cannot grasp all the information. Try to look at the example and try to understand the process. Okay. Okay, then I'll stop here, stop sharing, and only 8 of you today, five didn't, 5 absent. Only 3 of them told me that they cannot come, so I don't know about the other 2. I'll wait for them to